Professor, you are so funny, ha ha ha. Professor, TJ just got back from Archidon in the Pleiades, and said he had a recipe from Pam Ishia he wanted to share. He sent a video.
This recipe was given to me by Pamisia. She's from Archidonia in the Aries of the Zantisa. That's the 7 sons of the Pleiades, the 7 sisters. She was gracious enough to give me this recipe. This is pre-prepared thin spaghetti that was boiled in with a tablespoon of canola oil. This is diced red onions, diced green pepper, diced tomato. We're going to use butter. We're going to use a dash of red wine vinegar, a little spritz of sea salt and black pepper. And there's a special seasoning here that you can't buy anywhere. You could make it yourself, but it's called blackened sugar garlic. And I'll give you an idea of how that's made. You have to use a blowtorch in a black frying pan. Of course, sugar and powdered garlic, and a splash of vinegar, and then you torch it until it crystallizes, just crystallizes, and you regranulate it and grind it up in a jar and pestles. Because it turns into a crystallized sugar that has to be ground up again, but it's got a blackened taste to it. So you only use a dash of it as a final garnish, but we'll show you that towards the end. With the range on high, we're going to melt 2 tablespoons of butter, a small dash, about a half a teaspoon of red wine vinegar, not much, it's just to make it a little sour, a light grind of sea salt, healthy amount of ground black pepper, this is all brought to temperature. It's going to be done very hot, very fast. Once again, the range is on high, and the butter is going to brown. We're going to cool it off with the vegetables very quickly. The cold vegetables cool the pan slightly. And vigorously stir in the butter and the vinegar, pepper, and light salt. Now once again, this is on high, so we're not going to take a lot of time. We're going to right to the point of where the butter begins to brown. We want the vegetables to be al dente and crunchy. Temperature's coming up. We keep an eye on the color of the butter. We don't want it burnt, we want it just slightly brown. I'm going to gather this. Turn off the heat. And set this aside. The frying pan is very hot still. We're going to add more butter, about a tablespoon and a half. Turn the heat back on high. Temperature's coming up quick. Then we're going to blanch, brown our already cooked spaghetti. Now that's going to happen very fast because we're on high again. And we want to take the butter to a point of being brown but not burnt. But you have to vigorously stir. You can see the color changes. And it would very rapidly go to burnt, so you have to be careful. This is where the special flavor comes out. And we turn the heat off, and our blanched, browned spaghetti is ready. See that nice brown, light brown color. Now we're going to set the table and we'll show you how to garnish. You know, TJ did all the cooking and he asked me if I'd show the garnish. So we got the table all set and the dishes are ready to go. And this is the way they eat it on Archidon out in the Pleiades. That's the Seven Sisters. They take the blackened garlic sugar and liberally put it across the top as much as you like. It's got a nice carbony taste to it.
Oh, Professor, that looks wonderful.
And then they add a scoop of vanilla ice cream.
Say what? Oh no.
Nice vanilla ice cream. And then, of course, chocolate syrup.
Oh no.
Not too much. And then something we thought it was a little strange, but found out it really tastes good, is dried tuna fish.
Oh, Professor. Oh no.
Sprinkled over the top. And then they add the piece de resistance, the maraschino cherry. See, they don't waste any time. They eat their dessert with their entree. You know, it's kind of fun. I don't know, but try it. You'll like it.
Oh, my Professor, that looks awful. I wish you would have let me in on the joke. That was a sneaky way to promote your science fiction novel, Dilation. Anyway, Dilation, a science fiction, by T.J. Jin, available on Amazon.com. Ha, ha, ha.
Oh, I'm sorry, Lucy. I couldn't let you in on it. Otherwise, I couldn't have seen that expression on your face when I put the dried tuna fish on the ice cream, you know? That expression was priceless. And you're right, yeah, it was a good way to get a plug in for the book for TJ there on Dilation, the science fiction. It's kind of like a real Buck Rogers story. It's really good. You'll enjoy it. Okay, class, let's get back to work. Now going on, we're going to see why light isn't fundamental with proof. That means it doesn't all move the same speed. Okay, Lucy, show them the pictures of the laser.
The speed of light is not fundamental, it is variable. And it is related to frequency but not dependent. It is purely the velocity and duration of the energy wave. The professor stated the equation to calculate the speed of light but said it is wrong. The problem is when you are trying to measure something, and you are not sure of the length of your measuring stick. Our standard of time is fixed by the decay of cesium. So, at issue is the measurement of the distance light travels in 1 second. Since he is saying each light travels at a different speed, where do you begin when the given, accepted velocity is wrong? In this analysis, the professor is using specific fixed parameters. The optical slit is 0.05 mm and lays horizontal, which causes a vertical interference pattern. The laser is aimed parallel to the floor. The target screen is 13.741 meters distance from the slit for all three laser colors. As a result, all parameters are fixed in all three samples. The only variables are the measured results. This drafting was done for analysis in a computer-aided design system. Since the drawing of a slit that is 0.05 mm and a target screen that is 13.741 meters away, only sections of the drawing can be shown. The final adjustment from experimentation of the speed of light rendered the value at 299,792 458 meters per second, and then formalized in 1983 by International System of Units. This really formalized the length of a meter, which then locked in the speed, but this was stated to be accurate to within 4 parts per billion, which is 1,196 meters or plus or minus 598 meters. So, if you are trying to measure something with a stick that is ambiguous in length, you have some work to do. You must understand, telling the physics world it is wrong comes with sweat from the brow. This is going to get complicated, but we will attempt to simplify. The geometry of expanding waves is symmetrical. There is absolutely no reason for a violet wave to act any differently than a red wave. The waves in water are the same regardless of frequency, and so is light. Let's magnify.
Now we had lasers going through a slit that's only 0.05 millimeter. That's thinner than this paper that books printed on. And then we got that shining through a slit that's only 10 millimeters from the laser.
That is 10 centimeters, Professor.
13.741 meters all the way to the wall. That's really a long distance where we get the interference pattern now. It spreads out really big so we can measure it. Okay, Lucy, show them the details.
The opening is a razor-sharp slit of 0.05 millimeter. The paper the treatise was printed on is thicker than this opening. As previously shown, no matter how sharp an edge is made, it is still round, right down to the atomic scale. Thus the laser light is reflected in tangential waves along the curvature as described in slide 165. Here the professor drew them as round waves to show how rather than one beam of light, you have two dispersing, from two edges, that cause two reflected lines, that interfere with each other as they travel through space. No matter what distance you place the target screen, the interference patterns show. You get what was described previously, as pinhole magnification. The professor placed the screen at a distance of 13.741 meters. That just happened, that is where the wall was, so he used it as the screen. It does not matter the distance, as long as you use the same distance for all tests. Again, it does not matter what color your light is, the geometry is the same.
Thanks, Lucy. Now here we go into the geometry of the different light waves, you know? It's just like the waves in water. It doesn't matter the frequency, the geometry is still the same.
There is a tangential flat wave that reflects at the curvature off of each molecule of the steel blades. One could say the resolution equals the number of tangents you could draw on the curvature of an iron atom or molecule. The incident angle produced by the two edges changes with distance, which is why it magnifies. With a laser it is very small in the main beam, which is why the center is so bright, but the divergence beyond that is large, as it crosses the edges and expands into space. Referring to slide 186. We will begin with violet. As you can see, each color is reflected, and diverges to produce an interference pattern that is unique. We say reflected because the beam is reflecting off the edges, it is not being diffracted like in a prism, and the index of refraction of the atmosphere at 1.0000293 is so small, that it does not apply here. Each color of laser produces a unique angle, where the waves are out of phase, reflected from the two edges onto the target screen. This angle where the dark area appears, provides a specific wave count from the source to target, and also the number of waves involved in the out-of-phase period. You will notice that it is a progressive process, that gradually goes out of phase, to full out of phase, to gradually back into phase. This is why it fades to dark, and back to light. The cosine of the angle to the dark area mathematically shows the hypotenuse length, which shows how the waves of the dark area had to travel a longer distance, which is why they went out of phase. A measurement was taken to the center of the second interference pattern. You will notice that each bright spot gets narrower, as each dark area lengthens. However, the center of each, both bright spot and dark area, measures the same value of progressive increase of the hypotenuse of the right triangle. This is not an index of refraction by any media, this is purely pinhole magnification, and the geometry is simple. Each color reflects off of the steel atoms of the slit, and produces a different angle at which the interference pattern lands on the target, and the reason is simple: the time it takes each frequency of light to reach the target by propagation velocity. So let's continue with the math. The best thing we have going for us is the laser. Our only limitation is that we can turn it on and off, but not modulate its frequency. The photoelectric effect, as it is called, is when light energy modulates an electrical device such as a photodetector. They have speeds up to the 100 GHz range, but with light, we are in the terahertz range, or 1.0 e to the 12 Hz with infrared, from 350 to 400 terahertz, and ultraviolet at 790 terahertz, and up. So, this is why it is stated that light is 299 792 458 plus or minus 598 meters. It was not till we were able to bounce lasers off the moon that we could get this accurate, but still the fastest detector leaves us with a margin of error.
Now in this next section, it's going to get really complicated, and I apologize. And for you people that are, non-science professionals, just sort of watch and go along with it, and see all the complexity that went into the exhaustive calculation to determine these things to be accurate. So we start out with the violet laser at 405 nanometers, then we got the green laser at 532 nanometers, and the red laser at 650 nanometers. Now we're going to look at the travel time for 1 meter, and then we're going to compare the cosine of the incident angle, the length of the hypotenuse, and the difference between the adjacent face and the hypotenuse. So it's pretty easy to calculate the number of waves per millimeter. That's just simple arithmetic. But then we get down to where we can calculate how many waves are actually out of phase 180 degrees. With violet light, it's 154 waves. With green light, it's 206 waves, and with red light, it's 251 waves that are out of phase in the dark area. And then we're going to work with 3 specific parameters. We're going to look at the ratio of the red to the green to the violet, and then the large ratio of the red to the violet. Now these parameters give us what we call the ratio of A, the ratio B, and the ratio C. Now Lucy's going to give you a breakdown on these complex calculations, and we're going to show them on the screen and let you review them and everything. And for those mathematicians, you can get a hold of a copy of the treatise and try to prove me wrong. That's going to be tough to do because I know I'm right.
First, we calculate with given wavelengths. With today's computers, the calcs are fast and easy. Do not be impressed by the numbers, but they are accurate and necessary. These next values use the velocity of light value of 299 792 458 meters per second. At this designated velocity, the violet laser is 405 nanometers at 740.228 and change terahertz. The green laser is 532 nanometers at 563.519 and change terahertz, and the red laser is 650 nanometers at 461.219 and change terahertz. Time to travel one wavelength for the violet laser is 1.35 femtoseconds. The violet laser is 1.35 to the minus 15 seconds per wave. The green laser is 1.77 to the minus 15 seconds per wave, and the red laser is 2.168 to the minus 15 seconds per wave. The cosine of the incident angle is shown, and is used to produce the value of the hypotenuse. The length of the hypotenuse is shown, as 13,741 millimeters plus. What will be used is the difference, which is simply the remainder when the adjacent base is subtracted from the hypotenuse. The values are shown here. The simple equation, c divided by the frequency, gives the wavelength, which gives the number of waves per millimeter for each color shown here. Red is 1538.46 waves per millimeter, green is 1879.699 waves per millimeter, and violet is 2469.136 waves per millimeter. Using this equation shown, Wc is the wave count, dc is the hypotenuse difference, and Wm is waves per millimeter. This gives the number of waves involved in the differential or out-of-phase dark region. The number of waves, in near 180 degrees phase differential, and this is regardless of the distance to the target screen, because the cosine and angle remain the same, is as follows. Violet is 154.66, green is 206.84, and red is 251.35. A simple observation is, if the velocities of each color were the same, then the number of waves out of phase that produce the interference pattern would increase, and not decrease. Violet should have more waves in differential and not less. Example, red has the most waves out of phase simply because it is slower, as its hypotenuse shows by length. Now, let's look at some simple ratios. First, the number of waves predicted by the given 299,792,458 meters per second. As with the sound waves, where we looked to find a synchronous wave at a specific frequency, but found it elsewhere, we are doing the same here, based against the expected and predicted values. To spare our non-professional observers the laborious analysis, the professor wants me to just give a quick summary. This analysis uses comparative ratios against the given erroneous light speed. The process produced errors that caused the natural centering of green light, within the span of red to violet. First, the ratios A, B and C are determined. Then the ratios of the incident angles are calculated, and labeled A', B', and C'. Next, the ratios of hypotenuse differences are calculated and labeled A, dual prime, B dual prime, and C dual prime, and finally the measured distance of the opposite side, or rather, the distance to the interference pattern ratios are calculated and labeled A triple prime, B triple prime, and C triple prime. Next, is the complex process of comparing the ratios. This is taking the ratio of the ratios. It is complex, because in the case of incident angles, as velocity goes up the angle comes down, which means you must reciprocate the A' and the A' values. Here are the calculations. First, the ratios of the measured millimeters to the interference pattern. Next, the ratios of hypotenuse differences. And, finally, the ratios of incident angles. So, now we apply the results by multiplying the expected wave count of waves per millimeter by the correction factor of the ratio of ratios. The professor used hypercalcs, but rounded off the large numbers to simplify. Applying the ratio means taking the calculated ratios of the waves per millimeter and adjusting them by the measured ratios of the other factors, incident angle, hypotenuse difference, and measured distance to the interference pattern. The corrected ratio is then multiplied against the denominator to unreciprocate, so to speak. This proposes an actual wave count of our measurement. First, the incident angle solutions. Next, the hypotenuse difference solutions. And, finally, the measured measured distance solutions. They are then entered into a database for comparison. This is where it was found that the data indicated the need to place the red-green ratio to the middle of the span between red to violet.
Yo. Let's see here. Hole in one. What do you say? Even professor's got to have some fun. Missed. Yeah, class, I told you this was going to be complicated. Lucy, let's see if we can simplify this a little bit.
The professor is insightful and knows, at this point you are confused, so let's look at one of the correction factors. The issue is, our base here is calculated by the erroneous velocity of light, which gives us an improper ratio, that the so-called ratio of ratios corrects, to give us a now correct value for the number of waves per millimeter for red light. The correction factor is then applied to find the number of waves per millimeter for the green by reciprocating the ratio. This is done for the B values, which is the ratio of green to violet, and also for the C values, which is for the red to violet ratios. Exhaustively, this is done for incident angles and measured differences to interference patterns. Next is the final analysis. This is the database where the green base is properly centered between red to violet. The general average shows the red trending down, with the green staying close to center, and the violet trending upward. Now, to apply this there are two possible ways. One is to say the frequency is to be adjusted leaving the velocity constant, but this is counterintuitive because the geometry of all electromagnetic radiation is the same. Thus it must fall on the velocity to be adjusted, to bring the number of waves per millimeter in line with the calculated. Because we know the velocity is in error, the equation here, c, speed of light, f, frequency, and lambda, wavelength, must give way to c equals frequency times wavelength. But the problem here is that our frequency was calculated from 299,792,458 meters per second. What to do? Oh, what to do? Well, here is the process. Take the mystery frequency from the database, which is waves per millimeter, and divide the millimeter. This gives us a wavelength factor. Subtract the wavelength of the calculated base set, to find the difference, and multiply that out to 299,792,458,000 millimeters. Confuse? Just watch. C, speed of light is 299,792,458, WL, calculated wavelength. cm, speed of light in millimeters, ct, true speed of light. Example calculating B12. This is 821.885 meters slower than the conventional velocity, but not far from the margin of error. Repeating the above equation for all data calculations that indicate a slower red velocity is shown. For data showing an increase in waves per millimeter, the equation is altered as addition. This example calculates B6 with 1,546.83 waves. B6 yields 1,546.83, which equals 299,793,512.2, that is 1,054.2 meters faster. The verification equation is to take the new light speed, divided by the original calculated wavelength, to find the new frequency factor, and divided by the calculated speed of light of 299,792,458,000 millimeters per second. B5 yields 1528.849 equals 299,791,232.79, which is 1225.2 meters slower. Example of B5 above using the verification equation. The checked result is the original number of waves per millimeter. Using this checking equation on all the data gives proof. We continue calculation for green. First is data that shows slower speeds. And data that shows faster speeds. Continuing with violet. It is interesting that there are no slower speeds for violet. In this analysis, the professor is holding the frequency constant, which shows velocity differences. Since frequency is determined from the equation, v, velocity divided by wavelength. Using a new speed of light would say the frequency needs adjusting. I.e., violet, from D7, at 299,794,620.01 meters per second, which is the largest increase, and using the equation, wavelength equals the reciprocal of frequency divided by the velocity, c, we get. Or using the equation, frequency equals the reciprocal of wavelength divided by c, suggests an either-or situation, but the professor thinks is it both. So, adjusting both the frequency and wavelength is the logical solution, since the propagation velocity is the primary value. I know this looks complicated, but the difference is so small it has been overlooked or not detected. Since frequency is velocity divided by wavelength, all must be adjusted, and on a cosmic scale this is a huge discrepancy.
So class, the modified equation for the light coming through a prism has been modified to put green as the center, 299,792,458 meters per second. So here we have the equation, which is 1 minus d1 divided by d2 times 0.001, and then times c, the velocity of light. And what this does, it adjusts the velocity, the change in velocity for all the colors that are yellow, orange, or red below green. You subtract the change, and for the true velocity, for cyan, blue, and violet, you take the speed of light plus the change. So all the colors are not traveling the same speed. The velocity of light is not fundamental.
Professor, now we really have a reason to dance. Yahoo!
Sure, Lucy, let's dance.